Hi, my name is Geoff Brooks. I'm a professor at Swinburne. I have been working in the field of pyrometallurgy for 30 years. It sounds like a very long time. I started off at high school with a great love of chemistry and maths, and that then turned into me doing a chemical engineering degree. And for a number of years, I worked as a practical engineer, and then I got the research bug, which is very hard to shake once you get the research bug. And I've had it ever since. The last few years, I've been really concentrating on the issue of how do you decarbonise steel production. And that's today what I'm going to talk to you about. If we're going to talk about decarbonising steel, we need to understand steel. Steel is obviously an incredibly successful material. And I just want to bring to your attention that the building that you're in is held up by steel almost certainly. You go on a train made from steel. The rails are made from steel. You're in a house with all the goods around you, etc., etc. So there's a tremendous amount of steel, obviously, in our society. And steel has a very large bearing on where you're up to in technological development. And so countries obviously value steel and they want to make sure that they have a good supply of steel. And the steel requirements they want change with time. They tend to go from long products, beams and rails, and as they get richer, they tend to head towards flat products, like the things you make cars and refrigerators from. Steel also makes a very significant contribution to CO2. So people estimate it's around about 10% of the CO2. And a lot of people think that it's the next cab off the rank after we've been dealing with electricity supply and also transport. So there's a lot of sort of social, political pressure around that issue, of course. There are basically 4 ways of making steel. We're going to highlight in this talk 3 main ones. The first one is the blast furnace route, where you basically bring ore and coke together into a furnace in a very hot place, and you make molten iron, which is an impure form of iron. And that iron is then refined in a BOF, and you make steel. There are other processes, but that's the main part. And it dominates world steel production, about 7% of the world's steel. It also dominates CO2. The next one, important one, is scrap recycling. So this is basically where you get scrap and you melt it down using electric arcs and then refine it and then cast it. And at the moment, this is about 20% of the world's steel. The third option is what's called direct reduction. You basically only go to a solid product in the iron making step. You don't go to a liquid product. And this means that all the slag and gangue that's separated out in the blast furnace gets caught up in the iron product. So it's like a low-grade iron. And this is often used with natural gas instead of using coke or coal. And this is then melted in an electric arc furnace. And this is at the moment about 10% of the world's steel supply. And everybody thinks that this is likely to grow in the decarbonised future, which I'll explain why. And then there's another technique called smelting reduction. And smelting reduction is so small, I don't think we need to spend much time on it today, but it's an attempt to make liquid iron without having to use coke, basically. Who makes steel? Well, there's about 1850 million tons of steel made every year in the world, and it's dominated by China, India, Japan, and the USA. We are very, very small players in the steel production game. So we have a couple of blast furnace plants, one in Sydney and in Whyalla, and they make 3 million tons in Wollongong and about 1.2 million tons in Whyalla. And we have 2 electric smelting plants in Sydney and Melbourne, and they're sort of at 0.58 and 0.76 million ton scale. It's very common that electric smelting plants are smaller than the blast furnace plants. They're often called mini mills. So that's part of the nomenclature in steel. We are, however, a huge player in the game of producing the ore that goes into the steel. And we dominate export of ores. And we're up around about the 900 million tons of ore. It's an incredible number. And if you go to Western Australia and go up to the north of Western Australia, around the Pilbara, you'll see enormous trains and trucks transporting vast quantities of ore. And of course, it's a great generator of wealth in our country. One of the things that interesting that people ask is, could we go circular and just live on the scrap? Well, unfortunately, when you look at the scrap produced in the world, it's not really enough. It's about 40 to 50% of the requirements. In other words, we don't have enough scrap to make the steel. So we can't go circular. But there's also issues about the quality of the scrap. So there's scrap that comes from around the plant, which they call home scrap, and the manufacturing plants, which is called prompt scrap. And it's quite good quality. But the scrap from obsolete cars and bits and pieces of machinery, etc., are often very mixed and of poor quality. So that's one of the big challenges facing the steel industry, is how to deal with this tsunami of obsolete scrap coming towards us.
Steel is contribute to more than 7%, yeah, of the greenhouse emission. Yeah, so now in Australia, yeah, around 75% of the steel process is made through blast furnace and basic oxygen furnace. Yeah, so then it's only 25% from EAF, and we know that with using EAF is based on scrap. Yeah, so which means that we need to know how much scrap that we have in Australia, and also like the quality of the scrap in Australia.
All right, so what are the key issues? Well, I think first of all, we need to start off with the Paris Agreement on steel. So the Paris Agreement and the repercussions on the steel industry, it basically says that we're going to reach a net zero with CO2 by 2050 to try to prevent climate change. We're going to have to reduce the CO2 by 90%. And that is a very large reduction. So we could reduce the CO2 a lot by being cleverer and more efficient, and as engineers are very good at making things more efficient. But 90% is not something you can do by just being clever and changing the process a little bit. We're going to have to revolutionize the processes. So that's one of the important realizations that we have to make, because the steel industry for the last years, there's some big revolutions post-Second World War II, but since then we've just been improving the process, right? But that won't work for this problem. People have done calculations about the CO2 from different routes of steel, and the basic analysis shows that if we can shift from the blast furnace to some sort of route where we have the DRI, the solid one, going into an electric arc furnace and using hydrogen to make the DRI and renewable energy to fire up the electric arc furnace, that we can really dramatically reduce along to that level. So we can get like 80-90% reduction. So in a very simplistic level, this suggests all we need to do is turn off the blast furnaces and stick on the scrap, stick the DRI and the scrap into an EAF, and put on the hydrogen for the DRI and renewable energy for the electric arc furnaces. But as you'll see, there's quite a lot of complexity with doing that. One of the things to realize is that when you're looking at these routes, most of the CO2 is in the iron produced, is coming in the iron making step and the preparation of the feed materials. So the steel making is relatively low CO2. It's the iron making. And that's pretty easy to understand, because what you're doing is you're basically taking the oxygen from the iron oxide and putting it with carbon. Our part of it, as I said, is very significant because we are the world's largest iron ore exporter. Iron ores are complex materials, you won't be surprised to know. There are really two major types. There are magnetite ores, Fe3O4, which are magnetic, as the name suggests, and there are hematite ores, and these hematite ores are often combined with goethite, which is a hydrated form of iron oxide. And at the moment, we basically are seeing the grades of ore decrease with time. So you'd say like a high-grade ore was over 65%, and below 62% you'd say it's like a low-grade ore. And the gangue minerals in this, like silica and alumina, make a big impression on the post-processing of these materials. You end up with a lot of slag generation, and you may have trouble with quality. So there are issues in iron ores. They're not just all the same. A lot of the iron ores, I said, come from the Pilbara, where there's a lot of hematite goethite ores there, actually. We also are seeing these hematite goethite ores. With time, as I say, the impurities build up, particularly alumina and silica. One of the most important impurities is actually phosphorus. Phosphorus is really bad for the quality of steel. You only need a very small percentage of phosphorus in a steel to avoid the quality of steel is very poor. So these ores are heading southwards in terms of their quality. So how do we go green while we're dealing with this basically lowering of quality of ore from the big issues? People estimate that only less than 10% of the ores that are sold are in this high-grade area. So basically, the blast furnace has got really good at getting rid of these all these gangue minerals. So that's one of the big advantages of the blast furnace. So if we're going to go to a general green solution, we've got to make sure we can get rid of all the gangue minerals. That's one of the great advantages currently of the blast furnace. And it's naive to think that we could just do that straight away with the existing technology. Before we get into some of the details of hydrogen iron making, I think we need to take stock and look at what we're really saying here. So the summary I would put it is the following. At the moment in the world, we're making most of our iron, 90 to 95%, by getting iron oxide from the ground, putting it together with a form of carbon and some fluxing materials, making a liquid iron, some slag and some CO2. The other way that we make it is we get some iron oxide from the ground and we put it together with natural gas and we produce a solid iron with some water and some CO2. That's the other way. The two main ways that people are proposing at the moment to substitute for that is to introduce hydrogen. We know that hydrogen can also reduce iron oxide to iron. We know that works. We know it can happen. At the moment, it's a small technology, but we see prospects of growing it. So that's one obvious route, using hydrogen. At the moment, hydrogen generation is dominated actually from a hydrocarbon source, which they call blue hydrogen, which is essentially getting methane and breaking it down. And this will generate CO2. So that's obviously not the long-term answer. People are trying to promote green hydrogen, but as it stands, green hydrogen is at very small production rates and it's currently already quite expensive at the moment. And people are hoping that we can get the costs down, but it's a major challenge. So basically, to give you some sense of where we're up to scale, for a steel plant, you need gigawatts of hydrogen production in terms of electricity usage. And we're currently producing things around more like the megawatts. So this is a big issue. How do we scale up this technology? I suppose who's also paying for it is a big issue. And as I said, the cost. So at the moment, the cost at the moment in the world, green hydrogen is selling between $4 to $12 per kilogram, US dollars. And at between 4 to 12, you're going to double or triple the price of steel. So obviously that's a very big consideration. And people are trying to find ways to reduce the cost. It has a lot to do with scale. And there's also quite a lot of policy discussions going on at the moment about maybe the government needs to intervene in this stage when you are trying to bring in this green revolution. So these are, people are hopeful that in 10, 15 years from now, that hydrogen will be a much more reasonable cost, maybe $2. But even at $2 or $3, we are still got issues about, as I mentioned, the gangue and how the processes will work for these general ores. The next obvious one is using electrons, which is basically saying using electrochemistry. So using the kind of processes that we see in a battery, but in the reverse and during the electrolysis, we can also make iron. That we know that's scientifically possible. At the moment, that's really at lab scale, but there's quite a lot of work going on at the moment trying to make that to bigger scale. There are then two other kind of ideas that you could also use in addition to those two chemical solutions. One is to say, all right, well, it's really difficult to get rid of carbon. So instead of replacing the carbon, why don't we get the carbon from a sustainable resource, like, in other words, some biomass? So why don't we grow carbon and only consume the carbon that we grow? And then you could argue that we're creating a circular carbon type steel industry, right? That's one approach. Another approach is to say, oh, well, why don't we just capture the CO2 and either store it in some safe underground facility or utilize it as a product. So I'm going to be mainly emphasizing the hydrogen in this talk, but explain a little bit about those other ones. And the reason why I'm emphasizing the hydrogen one is because, to be honest with you, I think it's the most likely one. So let's have a look. I think we need to start off looking at, well, could we bring hydrogen into the blast furnace, right? That's a pretty obvious question. All right, do we need to get rid of the blast furnace, or could we introduce hydrogen into that blast furnace? When you look at a blast furnace, it's an extraordinary development. It's been developed over 300 years. And in a blast furnace, you have this big tall column up to 100 meters high. It's an impressive device, piece of machinery. And you have layers of iron ore and coke descending in a column. And you have hot gases coming from the bottom, which they call the tweer line, where they inject these gases, where it gets over 2,000 degrees C. So this is serious pyromania going on here. And what you do is you get really good reaction going up this column as the ore descends. The coke it plays a very special role in this column because it not only does it fuel the process, but it also provides the CO gas for reducing the iron oxides. But it also provides mechanical structure in the column. And that's one of the big challenges, because if we bring hydrogen into this system, what will provide the physical structure to the column? Because if you don't have physical structure near the bottom, you're basically trying to inject gases into a whole lot of molten materials, and it probably won't work. You may be interested to know that we used to use charcoal, and when we used charcoal instead of coke, they had to make the vessels much smaller because charcoal is not as hard material as coke. So this development has seen all these develop very well how to prepare the feed materials to make this reactor blast furnace work well. And unfortunately, it involves probably the least desirable part of the current steel process, which is the coke making. And coke making is basically getting coal and heating it up into a retort and holding it for up to 1,000 degrees for quite a few hours. And it creates a lot of volatiles. There are issues with pollution from coke ovens. So coke ovens are not a desirable part of the process of steelmaking process, and also contribute to the CO2.
So Infrabuild is a electric arc furnace based steelmaker. We have 2 electric arc furnaces, one in Laverton in Melbourne and one in Rooty Hill in Sydney. They use steel or scrap steel as the ferrous source, as the source of steel that goes into it. So we're very different from a blast furnace manufacturer, and because of that, we naturally have an advantage because we're a lower emitting process in terms of steel making. We very much understand that there are 3 major energy inputs that contribute to our emissions. The main one of those is the electricity we use to make the steel that comes out of the electric arc furnace process. The second is our use of natural gas, and the third one is our use of coke, which comes from coal that is dug out of the ground. For each of those, we understand there is a journey for us to move from grid electricity, fossil fuel-based electricity, to renewable. The second is around partnering with industry, with regulators and government, around being a long-term customer of alternatives to natural gas. And for us, that's primarily a biomethane product. And the third part, where we currently use coke that's made from coal out of the ground, we're transitioning to using forestry byproducts, essentially sawmill and logging offcuts that have no other use, where we can turn them through an industry partner that we are developing a technology with into a biochar, so a coke replacement product that stops that from being a product that's derived from coal out of the ground to a renewable product that comes from the byproducts of the forestry industry.
One of the most important things to understand about the hydrogen approach also is that the reactions associated with carbon are exothermic. This means that when you react them with the iron oxide, you're giving out heat. All right? But the reactions with hydrogen are the other way around. They're endothermic. That means they require heat. So just replacing the carbon with hydrogen in the blast furnace will change the whole heat balance of the furnace. And that's not a trivial matter. And there's been quite a lot of work going on. And in Germany, ThyssenKrupp have been doing experiments putting hydrogen at the tweer line of their furnaces. And they found that they could get some hydrogen up to a certain level, but at a certain point, it doesn't work because essentially they are cooling the furnace down too much, in essence. And when you look into current research, people are saying that, well, you may be able to replace, say, 14 to 32 kilograms of hydrogen into the furnace before you start creating problems. And you may be able to reduce the CO2 from up to 30%, which is not anywhere near the 80 or 90% that we're talking about that's required. So as it stands at this moment, it doesn't look like we can get the hydrogen into the blast furnace. Now, I should say watch this space because I think there's still a lot of innovation that can go on in this area. And I know I'm aware of research, something that I'm involved with, trying to save the blast furnace to see whether we can push up higher. But as it currently stands, there is some skepticism about that being possible. I should tell you that the blast furnace death has been long predicted for many, many years. It's extremely resilient technology. And people don't just easily bulldoze this technology, which they put so much money into. So that's another thing. There's so much capital tied up with the steel industry. It is difficult to just bulldoze something and say, let's try another technology. And until the arguments are compelling, and you can see around the world a bit of pushback about doing that. Then we look at the DRI processes, and the DRI processes are currently several variations. There's shafts, there's fluidized beds, there are drums, techniques, kilns they call them. And these processes are quite well developed for natural gas in particular. And people say, well, let's just replace the natural gas of hydrogen. And that is a good idea. And one of the most famous processes, the Midrex process, the most successful of the shaft processes, is a little bit like the top part of a blast furnace. It's essentially got a shaft, and they put natural gas in, and they go through a reforming reaction, so they make CO and hydrogen going through the shaft. And this is well established. This makes a lot of iron in the world already. And this process has already been demonstrated for quite high levels of hydrogen. So, yeah, this looks like a ready solution, basically.
So hydrogen steel making is a very promising area, and we believe that very soon it can take over the industry, because we want to reduce the carbon dioxide from the atmosphere, and hydrogen can be a very useful tool in that, because it can be like we can replace CO2 by H2O. So H2O is basically water. So that means we can reduce a lot of environmental pollution on that.
And they already operate the Midrex with the hydrogen to CO ratios of up to 4. So in other words, almost 100% hydrogen. So this is really a well-established technology and the obvious way that companies would like to go trying to use hydrogen. I should tell you, these furnaces are not generally operating with high-gang ores. So we go back to that ore problem. So essentially, this has been developed for rich ores. It doesn't mean it cannot be used for high-gang ores, but it's certainly a part of the process that needs to be understood, the sort of research I do. There are variations of this, and one of the most interesting ones at the moment is the hybrid process, which is being developed in Sweden. And this essentially got a shaft process connected to an electric arc furnace, and they've been making essentially zero carbon steel using this at pilot scale. So this is already underway, and there's quite a lot of development in Sweden along these lines. They have very rich ores, and they also have cheap renewable energy, which is one of the reasons they can do this. There have been already hydrogen iron making plants running at industrial scale. There was one in Trinidad some 20 years ago that made industrial level iron using a fluidized bed process, a 2-stage process. There is one being developed at the moment in Korea called the HIREX process, which is a multi-stage process. And there is also one in Austria being developed as well. So there's a lot of work at the moment. The reason why they're going for these fluidized beds, just to explain something, in the fluidized bed processes, you can just use fines. You don't need to make pallets. You don't need to palletize the material. You can just get by with fines, which saves quite a lot of cost. And I'm happy to report that in Australia, we're also developing our own process, which is called Zesty.
This is the project I'm leading. So this is the exciting real Australian iron making project. So what we are doing in Australia, this is in Bacchus Marsh in Victoria. So it's our very genuine one. And we are building a new iron making process. So we have done pilots. So at this stage, we are doing, so this project is called Calyx, a company. And the process is called Zesty, and they are building the demonstration plant. So as they're building it and as they're developing it, they have lots of issues and things, which is very new, very natural for any process. development. So what we do in Swinburne, we help them develop it. So it is quite exciting. One is Australian, and then another thing is it is zero carbon emission. So that's also very interesting.
Right. So we've been talking about hydrogen quite a bit, but there are other ideas. And the most obvious one is electrolytic. So people have known for a long time that you can use electrolysis to break oxides down to metals and oxygen. This has been known, for quite some time, for 100 years at least. So, and this is the major way that we make aluminium. We do it in aluminium already, so it's already an established route. So there are three basic ideas going on at the moment. One idea is to do it in molten oxides at high temperature. So basically put the ore into a molten oxide, put electrodes in it, and make iron. A second idea is to use molten salt, to put the iron oxide and say molten chlorides at a lower temperature, say 900. And another one is to do it at low temperature using aqueous solutions and different acids and basic aqueous systems. Now, they all have their merits, and there's not a simple, obvious one, which one's the successful one. And this is a very active research area at the moment around the world. It's interesting because you can see that actually when you look at all the amount of stages and steps required for hydrogen DRI to make steel, these ones will have less steps. And the reason why is because you're not making hydrogen. So essentially, you can see sort of in this sort of argument that hydrogen is the middleman. It's basically, you're basically using renewable energy to make hydrogen, to make metal, where electrolysis route, you're just using the electrons directly. So there's an interesting aspect of these electrolysis routes. There are a number of developments going on. The one that I'm most familiar with is the molten oxide electrolysis. And Boston Metals, a spin out from MIT, is particularly associated with this one. And they've been working on doing this molten oxide electrolysis above 1600 degrees C. And you end up making iron and oxygen. And one of the big challenges is what to make the anodes. So you've got to have electrodes in this system. And the most challenging one is the anode. There was a paper published in Nature in 2013, which showed that the ferrochrome system was promising as an anode. I don't think ferrochrome anodes are the general solution, but this is where you get this, where you see this green revolution leads to other scientific developments, because we're going to have to do some very sophisticated material science to develop these anodes. And I'm aware of two projects in Australia at the moment, one of which I'm involved with directly, that's trying to develop anode materials. So that's an exciting area. These molten electrolysis routes, they still have a long way to go. They're very small scale at the moment. One of the repercussions of going this route is that instead of having one big large reactor like we have currently, or two with blast furnaces, you would have hundreds of electrolysis cells. And how you would couple these hundreds of electrolysis cells to the existing steel structure is not clear. And it makes you wonder whether the future of this is maybe on a greenfield site where you were starting from scratch and you said, right, let's just reimagine the steel industry. And that's why I think this electrolytic route could succeed. It's very difficult to imagine this being done at an existing steel plant because it's not really compatible with the current equipment. So that's a very interesting area of development. Another potential one is biomass. So this is based on the idea that I mentioned before, where, if we're growing either crop material or trees or whatever, a waste material as well as a possibility, could we use it in the steelmaking process to replace the carbon? This is not a new idea. This has been around a long time. In fact, steel used to be made from charcoal, not from coal and coke. And it's been well researched. And basically, to make it useful in the iron making stage, you'll need to turn it into a char. But we know a lot about making char. That's something that humanity's done a lot in. And the issue with char is that it's not as strong as coke. So this means that you probably cannot just directly replace it for the coke inside the blast furnace. But you can use it in all other parts of the plant. You can use chars. And there has been extensive research at trying char all over the steelmaking process. So as I said, well understood. What generally holds the biomass route down is cost and availability. So gathering up all the different biomass materials and then turning it into char ends up adding significantly to the cost. And I think also there's a political social aspect of it, because a lot of people would be objecting to people growing forests to make char. And there's also arguments about, how can you prove that you're bringing in the amount of growth from the forest to match the production of the plant. So, but I think where it could succeed is where you have obviously large amounts of biomass waste. That's where it could succeed. And there are people exploring that at the moment in Australia. Rio Tinto has a process called the bio-iron process. And their idea is to combine the iron ore with waste char and process it in a microwave heating system, which is very interesting, and to use that to make iron. And once again, I'm sure this can scientifically be achieved. I have no doubt at all. I've actually worked on something very similar myself some 30 years ago. But the issue is, can we get enough biomass to get anywhere near the scale of production that we're talking about? Another issue approach is to go for the carbon capture and capture or storage. And there is work going on in Belgium at the moment called the Steelmaking process. And what they're doing there is they're combining the off gases of the blast furnace with some biomass waste material, and they're generating a bioethanol. And this bioethanol is being produced at significant quantities. And this has been going now for a few years, which is quite exciting. I suppose the only hesitation you'd have about this is, gee, how much bioethanol do you need? And can it possibly take up the CO2 produced from a large steel plant? And I think that's true of a lot of these CO2 utilization technologies. Yeah, you can do this, and it's quite expensive to do as well. It's not a cheap thing to do. I think the Steelmaking plant costs €200 million, and it only processes a fraction of the CO2 from the blast furnace. But also, can you make, who's going to take all that material? So that is a sort of, I think, a partial solution. I'll be surprised if that's a general solution for the reasons I just described to you.
Steel is something that really important for human life. This is something that we cannot live without. So for making this steel production sustainable, we really need to find a new way to produce the iron making in a more environmental friendly process. Many of us are focusing more on the hydrogen's process, but there are very limited resources to produce the green hydrogens, and it still requires a lot of energy and a lot of money to produce the green hydrogens to be used for steel productions.
So I suppose, in summary, the challenges for hydrogen DRI: do we have enough renewable energy to make the hydrogen? Do we make enough green hydrogen, which is associated with the same thing? And how do we process these lean ores? How are we going to do that? Do we need to make pellets to put into these shafts, or could we just use fines and directly feed them into these DRI processes? So these are some of the things that researchers like myself are dealing with in this hydrogen revolution.
I think what we need is people who are very curious and people a bit brave, and they're very resilient. I think this is something you really need if you want to be involved in this. Resilient means you don't give up. You just fail one day, you show up in the next day, and you fail next day, you show up in the third day. So this is what we need, people, and also curiosity. And you don't have to really know a lot about this stuff. Like, for example, I have mechanical background. I didn't know about metallurgy that much. If you asked me 3 years before, I literally didn't know anything. So I was Googling as I was going by. So it's really fresh start. But when you get sucked into it, you learn a lot, and you are surrounded by people who knows a lot. So I think this is the thing. And as a group, the high temperature processing group is very welcoming. We celebrate diversity. We celebrate different kind of people, different type of people. And I think, and we also do a lot of knowledge sharing among ourselves. So I think when we have this kind of people joining in, you will be well supported anyway.